Hey everyone, and welcome back to my science studio. In today's lesson, we'll be diving into some practice problems on predicting the products of single and double replacement reactions. We'll be using our activity series and the solubility rules here. If you haven't checked out my last two videos on single and double replacements, I highly recommend you do that first because today we're just going to be practicing. And so I'm assuming you already know the basics. But anyways, let's get started. Now, before I solve these problems, I encourage you to pause the video and try them yourself. Then go ahead, press play, and we'll walk through them together step by step. Okay, so in the first problem, we have K, which is potassium, and it's written by itself as a solid. And this is just a quick reminder that anytime you see a metal written by itself, no subscripts, no charges, it's a solid. The only weird exception we talked about before was mercury, which is a liquid. But in general, metals by themselves are solids. So here we have potassium reacting with barium nitrate. And first, I want you to identify the reaction type. And you see, I recognize this as a single replacement reaction because we have our A, our potassium, reacting with Bc. Our B is our barium and our C is our nitrate. Remember, nitrate exists as NO3 with a -1 charge. It is a polyatomic ion, specifically an oxyanion. And remember, we treat polyatomic ions as one unit. So that's our C. But anyway, so a single replacement reaction should follow that you produce A, C, and B, where A kicks out B. So here we're comparing two metals, our potassium and our barium. So the big question is potassium strong enough to kick out the barium? So we go to the activity series. Potassium is all the way near the top, and barium is below it. And remember, as you go down my activity series, remember all teachers have different versions of this series, so I encourage you to use the one that your teacher gives you for your exams. But anyways, on my series, the metals become less reactive as you go down a column. So here, potassium is more reactive than barium. That means it's stronger and it will kick out the barium. So the reaction does happen and we are able to predict the products. And just as a quick reminder, if A is not more reactive than B, you would write no reaction. And that's really important. Don't waste time on a question predicting the products if no reaction is going to occur. That's a trap. But anyways, so let's go ahead and identify our ions. So potassium is in group 1, so it forms a +1 charge. Barium is in group 2, so it forms a +2 charge. And nitrate is an oxyanion, which has the formula NO3 with a -1 charge, as we said earlier. And now that we have all our ions written out, we can go ahead and start pairing up. So on the product side, we form AC, where A is our potassium and C is our nitrate. Crossing the +1 and the -1 charge, they end up canceling each other out, and we're left with KNO3 or potassium nitrate. And barium gets kicked out as a metal. And remember, when we write metals by themselves, we denote the state of matter as a solid or S symbol. And I always tell my students this little analogy. Imagine you're renting your apartment and you forgot to pay rent. And then this big, strong, Hulk looking guy knocks on your door. He's stronger than you. That's your landlord. You're getting kicked out. That's potassium here. But hypothetically, what if someone weaker shows up? Maybe like a sweet grandma. She's not kicking you out. Maybe she even gives you an extension on your rent so you can stay in your house longer. But, anyways, in that case, no reaction will occur. If that works for you, then great. If not, totally ignore me. It's okay. Now let's go ahead and balance. Remember, we have to obey the law of conservation of mass, which says that matter cannot be created or destroyed, it can only be conserved. On the left side, we have 1 potassium, 1 barium, and 2 nitrates. On the right side, we have 1 potassium, 1 nitrate, and 1 barium. Now, quick notes, I've said this before in a previous video of mine. If you want to keep the polyatomic ions together as one unit when balancing, like I am right now, you can. I just prefer to do a little bit less math, but if you prefer to split the atoms, so you split the N and the O and then count the atoms individually, you can also do that. You'll get the same answer. But anyways, I digress. So we need two nitrates on the right. So if we put a 2 in front of the KNO3, now we have two nitrates, but now we have two potassiums. So in order to balance the potassiums on the left side, if we put a 2 in front of the potassium on the left, now we're balanced. What about solubility? Well, rule number 3 says that all salts containing the anions, and it includes nitrate here, are soluble, and there are no exceptions. So remember, if something is soluble, that means it can dissolve in water, and we write the symbol AQ for aqueous. Potassium nitrate is soluble. Let's try this next problem, where we have lead 2 nitrate reacting with potassium sulfate. I say lead 2 because if you remember from one of my past lessons, I talked about that Roman numerals next to the metal denote the charge. And so lead specifically in this example has a +2 charge. And I know this because the 2 next to the nitrate, right, the subscript here, that came from the lead when the charges were crossed. But anyways, I digress again. Right away, I recognize this as a double displacement because we have two ionic compounds here. So this follows AB reacts with CD to produce AD and CB, where if you remember, our B and our D are going to switch partners. And remember, for a double displacement, we do not use the activity series, but we will use our solubility rules. So let's go ahead and identify our ions. Our A is Pb2 plus, and our B is NO3 with a -1 charge, our nitrate. C is potassium, or K plus, and D is our sulfate, also known as SO4 with a -2 charge. This is, again, a type of polyatomic ion, specifically an oxyanion, and we can treat it as one when we're balancing. But anyways, so our B and our D will switch partners. So now our A will pair with our D. So lead will go ahead and pair with sulfate. When we cross the +2 and the -2 charge, they end up canceling each other out and we end up getting PbSO4, or lead 2 sulfate. Our C is our potassium, and that's going to pair with our B, which is our nitrate. So when we cross the +1 and the -1 charge, we end up getting KNO3. And remember, positive charge is always written first. So it's not that you write BC, like the NO3 before the K. No, no, no. You write the metal first. Write the K, the potassium first, before the nitrate. So we get potassium nitrate. Okay, let's go ahead and balance now. On the reactant side, we have 1 lead, 2 nitrates, 2 potassiums, and 1 sulfate. On the right, we have 1 lead, 1 nitrate, 1 potassium, and 1 sulfate. Right off the bat, I notice that I have 2 potassiums on the left and only 1 on the right. So if I add a 2 as a coefficient in front of the KNO3, that changes the number of potassiums to 2. But that also changes the number of nitrates, which I have 2 now, making it balanced with the left side. So I'm good. Now let's check for solubility. You see, most sulfates, according to number 5, are soluble except when bound to an ion like Pb2+. And in this example, PbSO4, or lead 2 sulfate, came about because lead has a +2 charge and the sulfate is -2. So when we crossed the charges, they ended up canceling each other out. That's why we got PbSO4. So it's insoluble. Remember, when something is insoluble, that means it cannot dissolve in water and you have to write the solid, or S symbol. What about KNO3? Well, NO3 is nitrate, And according to rule number 3, all salts containing the anions, including the nitrate ion, are soluble, and there's no exception here. So KNO3 is aqueous, so we can write AQ. It'll dissolve in water. Now, because a solid forms from these aqueous solutions, this is not only a double replacement, but specifically it's called a precipitation reaction, where the precipitate or the solid that's been formed from this aqueous solution is the PbSO4. Now, our next example is a little bit more interesting. We have fluorine gas reacting with sodium chloride. I recognize this as a single replacement because we have our A reacting with our BC. However, this is a little bit different. We're not comparing two metals. We're comparing two halogens, right? We're comparing the fluorine and the chlorine, which belong in group 17 or group 7A of the periodic table. And I want you to always remember this. A metal can only displace another metal, and a halogen can only displace another halogen. Don't start trying to have a metal kick out a halogen or vice versa. So keep a note of that. And one thing I like to do for my students when they encounter a halogen replacement in single replacement is when you have your A reacting with your BC, your A has to be stronger than your C. The fluorine has to be stronger than the chlorine to kick it out in order to form Ba and C. So a little different, but hopefully that helps. So here we have to use the halogen activity series. And on my table, fluorine is higher up than chlorine, meaning it's more reactive and it will kick it out. So the reaction will occur. So the products, like I said it before, you have your B and A. Your B is your sodium with a +1 charge, and your A is your fluorine with a -1 charge. Crossing the charges, you end up getting NaF or sodium fluoride. And you also produce C, which is your chlorine. Only remember, just like fluorine, chlorine also exists as a diatomic element by itself, naturally. So you have to write the subscript 2 to denote that two chlorine atoms are bound together. Remember your mnemonic, have no fear of ice cold beverages. Very important when predicting the products and balancing accordingly. Okay, let's go ahead and balance, speaking of which. So on the left, we have two fluorines, one sodium, and one chlorine. On the right, we have one sodium, one fluorine, and two chlorines. So our fluorines are not balanced. We have two on the left and only one on the right. So if we put a 2 in front of the sodium fluoride, now we have two fluorines on the right, making it balance with the left. But we also change the number of sodiums because now we have two sodiums on the right. So we got to go ahead and add a coefficient of 2 in front of the NaCl to make the sodiums balanced. And now we're good. The last thing we do is check our solubility rules. According to rule number 1, all salts of alkali metals, so those in groups 1A of the periodic table, like sodium, are soluble. So we write aqueous. And similar to fluorine, chlorine also likes to exist as a gas. Okay, guys, let's go ahead and try the last one. So here we have potassium chloride reacting with silver nitrate. And we recognize this as a double displacement, right? Where we have our A is our potassium, our B is our chlorine, our C is our silver, and our D is our nitrate. So once we write down all the charges, we can go ahead and start pairing up and then crossing charges. So on the product side, we form AD. Remember, our B and our D's, they swap places. So our A is our potassium and our D is our nitrate. Crossing the +1 and the -1 charge, we end up getting potassium nitrate or KNO3. And we also produce our Cb, where our C is our silver, right, Ag+, and our B is our Cl-. Remember, you always write the metal first. That's why it's Cb and not Bc. Okay, so we form silver chloride. Fantastic. And I'm looking at this, and we are already balanced here. So we don't need to do anything else. All we got to do now is figure out our solubility rules. We've already established that KNO3 is aqueous from problem number 1 and problem number 2. But what about AgCl? Well, according to rule number 4, all Cl negative ions are soluble except when bound to an ion like silver with a +1 charge. And because Ag plus is one of our exceptions, this is not soluble, it's insoluble. So it will not dissolve in water and you form a solid. And that's all for today. Thank you guys so much for watching. If you found this video helpful at all, please don't hesitate to like and subscribe to my channel. And don't forget to check out my community page for extra weekly practice problems. Until next time, happy studying.